In this video, we will be discussing the terminology that is used to describe atoms and differentiate elements from each other. First, let us discuss the size of an atom. If you scale the nucleus of an atom to the size of a blueberry, then the outer edge of the atom would be about a football field's length away. The atom is composed of three types of subatomic particles. The proton and neutron are located in the nucleus of the atom, while the electrons are located outside the nucleus. The protons and electrons are electrically charged, but these charges are identical, just opposite polarity. The electrons are also significantly lower in mass than the protons and the neutrons. We can describe any atom with three values. First is the atomic number. This is the number of protons in the nucleus, and this gives us the identity of the element. This number is constant and is often omitted because it is implied by the element symbol. The mass number is the sum of the protons and neutrons in the nucleus. This identifies what isotope of the particular atom you have. Last is the charge. For most atoms, this is 0, meaning the atom is electrically neutral. However, if there are fewer or greater electrons than there are protons, the atom will have an electrical charge. The element symbols we use to designate the 118 elements on the periodic table are typically abbreviations of the element name. For example, you have C for carbon and Ca for calcium. A small number of element symbols don't match the English name of the element, but most likely come from an older Neo-Latin name for the element. All element symbols are either one or two letters. The first letter is always capitalized. All 118 elements are organized into the modern periodic table. The table is organized in increasing atomic number. We will discuss the finer structures of the table in a later video. When discussing the mass of individual atoms, we need a unit much smaller than a gram. The recognized unit is the unified atomic mass unit, abbreviated with either a U or the symbol AMU. This is equivalent to the older unit Dalton. Some disciplines, such as biochemistry, still use the Dalton as their preferred unit. It is equivalent to the unified atomic mass unit. The unified atomic mass unit is defined as being equal to 1/12 the mass of a single atom of carbon-12. Each element has measurements for stable isotopes in nature. Each of these isotopes constitute a percentage of the naturally occurring element, and the relative or average atomic mass of the element is the weighted average of all stable isotopes. These values have been determined through extensive sampling and measurement, but could vary in highly local conditions. These values could also differ in other locations within the solar system or beyond. We just don't know because we haven't been able to do extensive sampling in those places. That is why these are called empirical or experimentally determined values. The relative or average atomic mass is determined through what is called a weighted average. A weighted average is one where the percentage of the total for each value is taken into account. In the example, you have two isotopes of boron, one with a mass of 10.0129 AMUs and one with a mass of 11.0093 AMUs. The first isotope represents 19.9% of the total, and the second is 80.1% of the total. You multiply the mass of the isotopes by the decimal version of the percentage, and then sum the values to get the relative or average atomic mass for the element. Here is another example of relative or average atomic mass worked out. In the problem, you are given three isotopes with 3% abundances. To determine the relative or average atomic mass, you multiply the isotope masses by the decimal form of the percent abundance. The resultant values are then summed to get the relative or average atomic mass.